Okay, yeah, I am Olof Åstrand, and I made a GitHub repo where you can find these slides and code that I will show you. And something about me, I'm currently working at Neonode, and we are working on a driver monitoring system that uses some neural networks. So I thought I contribute to this C++ meetups with some talk about neural networks and C++. And all the opinions I express here are only my own. I'm not. Don't blame Neonode. So this is what I will talk about. I'll check the time also. Because it's a C++ talk, I will talk a little bit about what is new and coming in C++ standard related to machine learning. And I will talk about some C++ libraries. And I will have a speed run through how neural networks work. I don't know how many here has been working with neural networks. That know and use it, maybe a little bit, not so much. Okay. Yeah, and at Neonode we are using convolutional neural networks because we are doing computer vision. We are doing driver monitoring. They have a camera in front of the driver that detects if he is falling asleep, and then he can get a wake-up call. And then I will go through a simple example in C++, PyTorch and TensorFlow of how to train the Sinus function. It's not particularly useful, but it's very informative. It's a simple example. Okay, so we talk about the new extended floating point types that is now part of C++ 23. And it's a pretty big deal because there has not been any new types in C++ in 40 years, so it's mainly this one. Maybe I should use this one, yeah. The brain float is typically used in machine learning. The other types already existed, but they're not, yeah.
Sorry, what's the difference between the B-float and float 16?
Oh, the B-float is more adaptable. Like in machine learning, you usually use numbers between 0 and 1. So it gives you a better range for this. But otherwise, they are the same size, but it's better for machine learning. Okay. And there's also the mdspan. And if you compare to the regular span, it's multidimensional, of course. And the span is just a pointer and length, but very useful. But unfortunately, the guy who wrote this suggestion, he wanted a sub-mdspan, but it was not accepted yet, but it will be in the next version, hopefully. And also, we have got the new multidimensional subscript operator, and that allows us to use two x and y. Most C++ libraries, they have workarounds for this, but in C++ 23, now you can use x and y for operator. Yeah. Also in, okay, yeah.
Can you have more than two?
I think so, yeah, but yeah, it can use more dimensions. But I'm not really sure.
And what's the usage? Is it like are they separated by comma inside the square brackets?
Yeah, exactly. You can have a comma in the square brackets. Before this was accepted, you couldn't use that one. You can only use one. So they use a lot of workarounds. But maybe someone knows if you can have more than two. I would guess so. Yeah, and also they started with a span but not the actual container. So for C++26, they will also include the container, not only the span. Yeah, and also we will have linear algebra. It's based on BLAS, and it's good to have some standard for this. Of course, there exist a lot of libraries, but it also is always nice to have it in the standard. Okay. Also, there will be a SIMD library. It could be useful to have, SIMD, single instruction, multiple data. Yeah. Also, execution, it's very interesting. And NVIDIA has a reference implementation, and they also have it on the Beeman project, I think, a reference implementation. But they think it can be useful to execute code on like a GPU or some other. Yeah. So it's called sender, receiver, scheduler. It's interesting if you want to learn more. Also, I think the network, it's not in C++26 because of this. They're waiting for something like this to drive the execution and scheduling of the network library. Mm-hmm. Yeah, and this is a hallucination from the AI. It's not a real, it's not a real class, but it's interesting that one day the algorithms might kill us all. A bit scary. Okay, so we talk about Python. Of course, if you are serious about machine learning, you have to learn Python. But when you look at all the libraries, they are all, most of them have their core written in C++. So it's good to know C++ if you want to get into the core part of the libraries. So I will just go through some libraries that's good to know about if you're into machine learning. So NumPy is, of course, fundamental. And TensorFlow is written by Google. It's a Python library, but it's also implemented in C++ in its core. And also has a C++ API direct interface. I tried to make some example with this one, but it's not so easy. If you want to do training, I think you have to stick with Python. But if you are into inference, you can make it C++ only. Yeah, and also you have to know about Eigen. It's a good C++ library for linear algebra. It's been around for quite a while. And it's also interesting, these new features that will be in C++26 and 29. It will, of course, take some time before it gets to these libraries, but hopefully they will be better and more easy to use. Also, we have mlpack. It's an in-memory library to share models between frameworks, so you can load them in memory and save and handle them a little bit. I was working a lot with Apache TVM, and they use mlpack. Yeah, and also mlpack, I haven't tried it, but it's a header-only C++ machine learning library. And of course, Armadillo. So now we don't have to use it if we get linear algebra in C++26, but it's been around and it's used in mlpack. Yeah. Okay, so yeah, I'm skipping, running through this quickly, but I like a lot of information. But if you have some question or think I'm going too fast, you can maybe stop me. But now I will talk a little bit more about neural networks. It's smaller than the whole machine learning area, but the main thing about the neural networks is that you train them, and they are normally you can see them as a graph. So if you're interpreting, or if you're running inference, you're executing a graph, basically. You run the tensors through the graph. So if you want to visualize, you can use a program like Netron. This is just an example of Inception, one of the earliest Inception models. Yes, and we talk about deep neural networks. They are modeled from biological neurons. So the idea was to look at how a biological neuron works. And you create an artificial neuron that is similar but not the same at all. But a lot of features you can find here. You have the inputs and the weights, and you have an activation function. And this activation function is very important because it introduces the non-linearity in the system. Otherwise, it would be not so easy to train for more complicated tasks. So if you're doing vision, for example, then you have the input layer is like the pixels on the screen, and you can see the tensors, the values represented by the intensity in the picture. Then you have the hidden layers and the output layer. And the activation function is normally one of these three, or these are the three most common, the sigmoid, tan, and ReLU. And it squeezes the output to a number between 0 and 1, and this one between -1 and 1. Okay, so we have an example. I don't know if it's too early to run this now, but it's a good illustration of how. Let's see if we can do it. Okay, it's already here. Nej, det var ju inte så bra. Okej. Ja. Ctrl-Shift-T. Får man tillbaka det gamla då, eller? Tack. Thank you. And don't press the X. And try this one. Okay. Okay. You can have full screen also, right? Somehow. Exakt. Men nu är det en Chromebook här. Men den har en knapp för det. Ska det finnas någon? Kan det vara en? Okay, so this is an example of a neural network. It's very simple. It's a classifier. So here you can see the input data. So this will take X and Y value and classify as yellow or blue. And you can increase the number of hidden layers. Okay. And here you have the activation function. We could maybe use ReLU. And we start training. Also here you see the batch size, how many you do at each. But it says here, ratio training. Oh, this one, the ratio training. Normally when you do neural networks, you use some data for training and some data for verification. So here you can remove the test data. So the test data is what you test your network with after it's been trained. And normally you run each training round, you call it an epoch. So up here you can see how many epochs you have run. And here you will also see the cost function, how good is the network. So if it's good at training, it will go down to 0 pretty quick. Yeah, so here you can see the training runs for only a few epochs and it goes to 0 really quick. So we can try a little harder example. This one. It's a... yeah, here we have all the blue dots close to the center. Okay. Okay, so we go back to the presentation. This one? Okay. So we have to start from the beginning. Yeah. Okay. Good. We didn't have to start all over again. So, yeah, you've seen the training of this. It was a very simple example, only X and Y input and blue and yellow. But when you do training, you either do supervised training with labeled data, unsupervised, or reinforcement learning. That is, you are rewarding desired behavior and punishing the undesired behavior. So this is like the cost. And then you have a GPT, which is like in between. You use unsupervised training in the beginning, and then you maybe use labeled data at the end. Okay, but at Neonode, we don't do so much simple neural networks. We use convolutional neural networks, which is better for image recognition and natural language processing. So, and in the convolutional layer, you do something what you call it's like a feature extraction. Like this input image. You have a this is not a very good example, but it's the eye. So you will run this convolutional layer over the input image, and you'll get an activation map to where the eyes are found. You can see that it's like a feature extraction. Okay, so I'm not going to do the demo. If you compare it to our brain, the amount of neurons, a brain is about 86 billion neurons. And of course, a parameter is not the same as a neuron, but it gives you an idea of how many neurons there are in a brain, 86. And the latest one, DeepSeek R1, is about 671 billion, but they are using a mixture of experts, so it's like separate networks. The input is routed to the expert that the network think is most suitable to handle the input. Yeah, so this is generative pre-training. To feed the network firstly with a lot of text, but not so much labels and context. It's just for pre-training. And then after pre-training, you do the fine-tuning. Okay, so this is the amount of data that was used for GPT-3. And it was estimated that it cost about $20 million to train this one. But of course, you can do it for $30 if you're from China. I don't know. Yeah, but I think it's easier when you extract data from some other model. It's probably cheaper. And also if you're lying about how much it costs. But yeah. So this is like a picture from the DeepSeek mixture of experts. You have the shared expert that always look at the problem, and he finds who is the best expert to take the problem. So it's called the routing of the problem. Yeah. Yeah. Of course, when the networks becomes really good, we will have a problem with alignment, and I just wanted to make us all remember this. It's going to be a problem when we have created something much more intelligent and maybe more powerful than us. If we can't pull the plug, we will have a problem. And also, you have to know about the singularity. The last invention we have to make is a really good AI that will make all the rest of the inventions and also improve itself. So, yeah, also you have to know about AGI. So when the AI becomes better than a human to understand and learn new things. Yeah, this is not AI. Yeah, okay. I'll talk a little about machine vision and object detection. So it's a bit different from what we talked about before. But you would like to find objects of interest in an image. So it will find the bounding boxes and like a number to how certain you are that you have classified this as a vase, dining table, and wine glass. Yeah, and this is the way you do it. You use this convolutional network. So this will be a 28 by 28 pixel input as a handwritten number. You start while running it through convolutional network and then pooling. Pooling will, like a max pooling, you will lower the resolution. And then in the end, you run it through a flat and normal, like I showed you earlier, fully connected network. Okay, so I'll talk a little bit about Apache TVM. So this was the idea of the talk in the beginning, but it's very specific, so I want to talk a bit more general about neural networks and C++ instead. But Apache TVM can take the most commonly used formats for these models, like PyTorch and TensorFlow and ONNX and Keras. It will read the input like a pre-importer, and then it will use its own language. It's a highly differentiable IR language. Okay, not so. Like this. It's called relay. So you import the model. This is PyTorch and TensorFlow. And you go to relay language. It's like this network of operations. It's a graph of operations. And then it will translate into tensor IR. If you worked with LLVM, you know about intermediate representation. And then you can, TVM does this auto-scheduling that tests different combinations to see which one is the fastest. And then you will use LLVM at the end to generate the machine code. So how to do it. Okay, so now I will go through an example in C++. This is the Sinus training. And I thought I illustrated with a picture, but maybe it's not so good. But it's a fully connected hidden layers of N neurons. And it uses sigmoid for activation. So Sinus will take a single value and output a single value. It's just a simple function, but we will train the network to represent Sinus. So, okay, so maybe this is a better picture. Single input, single output is between 0 and 1. And it will use the sigmoid function to do the nonlinear part. So here's the C++ code for the neural network function. It just takes the weights and an offset and run it through the sigmoid and output the result. So, and here we split the data into training and test data. And then we run it through the activation function. So in this case, we're using the sigmoid, and it's particularly useful in this type of context because its derivative is very nice. You can see it here. Yeah. Okay. So if you run the training, you will see the loss function going down, and here it's not converting, it's moving around a bit, so it's stop training a bit earlier. So this is how you do it with backpropagation. You calculate the prediction, and then you look at the error, and you calculate the loss function. And if you're using backpropagation, you're using the derivative of the loss function to find the direction where the loss function decreases the most. So you try to move in that direction. Okay. And this is how you update the parameters after you calculated the gradient. So this is the weights and the weight from the first and the second layer. Yeah, and also this is important that we also saw this in the example, the epsilon. It's how big steps you take for each epoch for training. So this in this scene example, you have this training set, and you look at the validation loss, and then the end result is this function approximation. Okay, so now we've done it in C++, we will see how you do it in PyTorch. So PyTorch is made by Meta, Facebook. They've done this framework for machine learning compared to TensorFlow, which is made by Google. So this is how you define the network then in PyTorch. You have a single hidden layer of size 16. And then you apply the sigmoid on the network. So this is a forward step. And this is how you would do the training. And in this case, we're doing 7,000 iterations for the training. And this is what the result would look like. Yeah, and if you visualize this with Netron, you can see the network here. We have just a general matrix multiplication, 16 fully connected layers. Yeah, if you're into machine learning, you can have some use of Netron, especially if it's a simple network like this one. And this is how the relay IR looks in Apache. If you have used LLVM, you can recognize it's very similar. And you see all the functions it's a graph represented as a text here. Yeah, and now I will show you how it looks in TensorFlow. It's similar, but you use keras to create the network. And you feed it through 16 neurons. And use in this case, we use, actually, we're using sigmoid. So the text is, this is the problem with documentation. It's always out of sync with the code. Just okay, so here I show the graph on the other way, vertically. No, horizontally, I don't know. So it's the same function, but in TensorFlow instead of PyTorch. Okay, similar results. And this is the, and if you remember the other one, you see it's very similar, but maybe you forgot already. No. Okay, actually, I think this is the last slide, but I will show also if we have any time left. Yeah. Yeah, we have a little time, so we can see at the code space. If you haven't used GitHub code spaces, you should try it. It's very nice. Especially if you have a not so powerful Chromebook like this, you can. Okay, so if you used Visual Studio Code, you can see we are now running it in the browser. And this white theme is not so nice, but you have this, what do you say? Yeah, the dev container. I try to fiddle a little bit with the dev container to run TensorFlow inside of it. So we can try an example. I already compiled this one. See the. Yeah. Also, I think this maybe is more fun example. Yeah, this one uses standard execution from C++ 26 together with, okay, this is not good. Can we make it bigger? No. Okay. We will just run this.
This is shutting down here.
Okay. Okay, no one can see anything. Not even me. So this is probably not the most good example. But anyway, I show you the GitHub repo and the code space. You can run your own and try it if you want. So I guess that's it. Sorry, I was a little bit early, but I speed run this one. So.
So you jumped over a microcontroller slide. Maybe you can.
Oh yeah.
The content to it.
Okay, which one was this one? Yeah, I didn't think about it because normally when you use Visual Studio Code, you can make the fonts a lot bigger, quickly, easy. But this one wasn't so good. But I'm sorry, I don't understand what you say. I skipped some slide. Okay. Yeah. This convolutional. Okay, the STM32. Yeah, this one. I've been waiting for this one for many years now. I think it was over here or over here. STM32. No, it's down. Yeah, it's this one. This one. Yeah, you are using this STM32. It's very popular for hobby projects. I'll use it. Visa fullskärm. I don't know. Fullskärm, är det sen? Längst upp. Bildspel. Okay, but then it will reset. I have to find it again. Now it's right. Okay, yeah. Oh yeah, they very recently released this one. It's STM32 neural network, but it's an ARM Cortex M55, so it has some enhancements for running inference on a small chip. So if you want to try it, you can do. Also, Texas Instruments has been doing this for a longer time, but they all have online cloud developer IDs, so you can train models and see how it's working. But I haven't started working with this yet, but I will very soon, so I'm looking forward to that. It used the ARM Helium vector processing technology. Yeah, also, okay. I can also, I think I have this convolutional neural network example. Yeah, this one. See how it goes. Yeah, it's kind of interesting demo. Yeah, I can do the full screen here. Full screen. Yeah, so this is a convolutional network where you have the kernel. It's called kernel, but it's a filter here. So this one will detect the top edge. So here is all -1, -1, -1, 1, 1, 1, and 0, 0, 0. So if you run this image, it's a number. I don't know if it's 0. Yeah, 0. If you run this one, it will detect the top edge. So we can try it. Yeah, we can step first. So you have, when you are doing convolutional networks, you have the stride. The stride is how fast how many steps this kernel will take over the image. And when you run it through this convolutional network, you get a smaller size tensor. We can play. Yeah, you'll see how it will run through the whole image. And when you detect an edge, it will give a strong output here. So you can see how it is extracting a feature. This feature is a top edge feature. And you can combine these networks together and make the graph so that you will help the network and detect what it needs for making classification or object detection. Okay, so that was.
So, just a question about this.
Yes.
Is it part of the training to tune these filters, or do you start out with a fixed set of these are good convolutions?
Yeah. What the experts they create the networks, but then you train the weights. But the graph is fixed. It's not something you change after. But
so the data flow is sort of fixed.
Yeah, the data flow is fixed.
Individual kind of kernel is being changed.
Exactly. Yeah. Normally, you don't fix the kernel. It is trained by the network, so it will learn what to look for in order to minimize the loss function.
So does it start out completely random, the same way as weights would be totally random?
Yes, you normally you do random, but also if you have a trained network, you don't train it from scratch all the time. You can start with a network that is good at recognizing images, and you can specialize. So you bring your own data to this and specialize it.
You can start with a generally good image detection, and then you apply it to
exactly for your special use case. Okay. Okay, thank you. So.
If there are not any more questions, then or other questions? No?
Yeah, okay. Yeah.
You were showing some slides with the Apache TVM.
Yes.
It has like variable type, and you were doing arithmetic on that. Is it like variable like y from some kernel like in TVM? And
I try to find the slide. Is this one or this one or no?
no, it's not TVM like shared pointer.
Aha, the code. Okay. Yeah. Yeah, this is
Before, yeah.
this one. Yeah. Okay. Oh, one more.
Yes, here we had like share point variable y.
Oh, yeah.
And there was subtraction we did. So like how many arithmetic operations can you do with it? And the second part of the question would be, are these automatically differentiated so that you get gradients directly?
Exactly. That's what the point of this shared pointer variable is, because you can use auto gradient. So in this case, it will make the derivative automatically. It's in the GitHub repo, and if the size of the font would be bigger, I could show you, but I'm sorry I didn't. And it's in this example, simple NN, I think. Let's see. Yeah, this one. Yeah. It's called bare metal or something. Yes, one of these one. You can look. Okay, thank you.
What was the GitHub?
Oh, the link. Yeah, I don't know how to share this one.
Put it on the video.
Yeah, he put it on the video, and maybe I can show you again. It's from the beginning. Yeah, okay. So it was a bit of a speed run, but I like to have a lot of information.
I think it was very good.
Okay, because people know about a lot of stuff, but not everything. Hopefully. Yeah. Here, yeah. This one. It's I'm Ebby roll. It's this sushi with a shrimp in it. I think.
Thank you.
Okay, thank you.